Having me here. It's my first time in Argentina, first time in South America. So happy to be here, and hopefully you'll like my talk. All right, so who am I? I work for a company called Independent Security Evaluators. I'm a consultant. You probably know me from I was the first to hack the iPhone, and I'll talk a little bit later about what I did. And then also first to hack the G1 Android phone, at least publicly. I wrote a Second Life exploit that was kind of cool. I won Pondon the last 2 years, and I wrote a book called Mac Hacker's Handbook, which if you should buy that, it's good. I make money off that. All right, so what's this talk? This summer at Black Hat in Las Vegas, I gave 2 talks, and this is basically a summary of the high points of both of those 2 talks. The one talk was called Fuzzing the Phone in Your Phone, about SMS vulnerabilities and exploits. And that's what most of this talk is about, just because I think it's kind of cooler. And then the other bit about this talk is about Meterpreter for iPhone. That's only the last few slides, and mostly because right now it only works on iPhone version 2, and so for iPhone version 3 I don't know how to do it yet. And so I don't talk about that as much. All right, so what am I going to talk about? Let's see what time it is. All right, so start off with just some iPhone stuff, and then I'll move into SMS, how you would fuzz SMS, and in particular how you inject messages so that you can do your testing. And then I'll show a bug I found and how I wrote an exploit for it using just SMS. And then, like I said, at the end I'll talk about iPhone version 2 memory issues and Meterpreter, which will be a good lead-in for the next talk, which is about POSIX Meterpreter. Okay, so iPhone, the way that the security is set up on it, it's actually pretty good. So these are all the features of the security, and I'll explain each. So the first is a reduced attack surface, and so what that means is they basically took off lots of useful programs. So it's like a Mac OS X box, except there's like hardly anything useful on it. So there's no shell. So for example, if you want to run shellcode, you can't just exec binsh. There is no shell. And even if there was a shell, there's like no ls, no rm, so there's no good utilities on the device. They also, like, their QuickTime is like very, very small, so it can't parse very many image formats or videos or anything like that. So there's lots of bugs that will be in OS X but not on iPhone, which is sort of the next part. And then code signing. So you can't just upload a program to the device and run it. It won't run. Only things that are signed by Apple will run. Randomization. So they actually don't have, there's no randomization on iPhone. All the addresses are only dependent on the version, so that's address of binary, library, heap, anything is not going to be randomized. Sandboxing, so just like in OS X, various programs run inside a sandbox that don't let you do things. So for example, when you download a program from the App Store, it runs in a very tight sandbox, so it can't dial the phone, it can't send SMS messages, that sort of thing. And even the Apple programs like Safari cannot run, cannot fork, for example, because of the sandbox rules. And then memory protections. So they have very, very tight DEP, so data execution prevention. So you can't just inject shellcode into the heap and expect it to run. It won't. And I can't remember if I go into more detail on this or not, but you cannot, once a page is writable at all, you can never turn it into executable. So it's not even like Vista where you could, do some trick to turn a page into executable and then jump to it. There's basically no way you can ever get your shellcode to run. So it's pretty good architecture. So where has iPhone been? In 2007 is when it came out, version 1, and it was not that great. So everything ran as root. There was no sandbox, no randomization, no memory protections, no code signing, and it was hacked within a couple weeks. So I actually wrote that exploit, and back then there was no jailbreaking, so there was no such thing as jailbreaking. So I had no way to like, get a shell to see what was going on. I had no debugger, and the fact that they had so little security meant I could still actually exploit it just by looking at crash dumps. And like I said, so there's at least 3 remote exploits that I know of for iPhone 1. 2 I did, and then there was like a libtiff one that people use to jailbreak their phone. All right, well, things changed a lot when version 2 came out. So that was in last summer. So mostly this wasn't probably because they wanted to make it more secure, but they wanted to have the App Store, and they want to make sure that you don't steal their money. So the App Store came out. They allowed you to write C programs, but you had to have them signed. And so this is when they introduced sandboxing, so that they could trust you to download these programs from the App Store. Dep no SLR, code signing. Now instead of things running as root, they ran as user mobile, which is sort of a low-level user, so that was good. Lots of security upgrades here. And then the trick at the end of the talk I'll talk about, there was a way you could get around Dep in iPhone version 2, but they fixed it in iPhone version 3 because I was stupid enough to talk about it. But the sort of the most important thing that you can take away from this is iPhone version 2 was out for 1 year. And during that year, as far as I know, there were no remote exploits for iPhone version 2. And that was even at Pwn to Own, $10,000 if you would have an iPhone exploit. And I didn't have one. No one else had one as far as I know. So iPhone version 3, which just came out this summer, not a lot of changes. They added MMS, so that's a new attack vector. They fixed the bug that I'll talk about in a bit. They didn't change ASLR. And so basically, if you think about it as compared to a Snow Leopard machine, it's actually more secure than the Snow Leopard machine because Snow Leopard has some ASLR, but basically iPhone has the Dep you can't turn off, and it has a much lower, smaller attack surface. So actually, your iPhone is more secure than probably any computer you would have. Okay, so that was iPhone. Now we move on to SMS. And I know Luis talked about SMS, so I'll go a little quick through this. So what's SMS? Basically, it's the command control channel for phones, mobile phones. So anytime you're about to get a call or you want to dial the phone, there's messages passed in this extra bandwidth. Messages are small, so 140 bytes, which works out to 167 bit characters. This is when people send text messages, this is sent over SMS. Some people think SMS is the same thing as text messages. Really, SMS is the protocol, and text messages are like an example. Because besides text, you can actually send binary data too. So you can send like ringtones or over-the-air programming, whatever. And I'm going to talk a lot about the different things you can send. And basically, this is like a very essential service that like all modern phones have. So the reason that I started getting interested in SMS is because basically, all these phones are, phones that, smartphones, they all handle SMS. There's no way to turn it off, or else you couldn't make phone calls or receive phone calls. And just like a nice server-side attack, I don't require the user to go to a website, right? I can just send an SMS, and as long as their phone is on, it'll get it. And what's even funnier is if you have your phone off and I send it, as soon as you turn it on, you'll get it then. So it's a great attack vector. And like I say here, it reminds me of back when I started into this. When I first started, there was no such thing really as client-side attacks. No one cared about that. Everyone just cared about hitting servers because that was, you could do it, and it was really powerful. And it's just like, this SMB exploit that the immunity guys have finished now. So it's powerful because you don't have to have the user do anything. And the other thing that's kind of cool is, like I might not know your IP address or your email address, but I probably know your phone number. So all I need is your phone number to send you the data. And there are firewalls and filters that especially the carriers can implement. But basically anything you put on your phone is going to work too high up on the stack to prevent any bad things from happening. So it's a very good attack vector. So that's how SMS in general. Now let's see how it works on an iPhone. So there's two processors. There's the one that runs all of your games and your web browser, and that's called the application processor. And then there's the one that you never really have any contact with. That's the modem, and that's the one that just talks to your carrier. So it runs its own operating system. That's it's just specialized. You don't know what it is, and it's responsible for communicating out. And the communication between these two different processors is done via logical serial lines. So you just send ACK commands. The application processor sends ACK commands to the modem. And then if you're just sitting there and an SMS message arrives at your phone, basically it just looks exactly like the text that shows in the bottom. So you get an ACK command, and then you get a number which indicates how big the data is, and then you get the data. And this is called PDU mode, which is more of a binary mode than there's another mode. I don't think iPhone supports it. That's just all text. And so you get these ASCII number or ASCII hexadecimal numbers, and it's interpreted as bytes at some point. So that last thing was some data. If we want to fuzz it, we need to understand the format of the data. So let's take a look. Here's one I broke out for you, and you can go through it and figure out exactly what each byte does. So the first thing is a 7, so that's the byte. It's a length field, and so this data is what they call TLV, so type, length, value, and these are good things to fuzz. So you get the size of the SMSC, so 7 bytes. You get the type 1, which I think is international number, and then you get the actual address of the phone number. It's encoded in some way. And then you get a byte that basically tells it that this is a message that's coming to the phone as opposed to leaving the phone. And then you get whoever sent the phone the SMS their data, so length, type, value. Then there's a couple bytes that are basically bit fields, and they tell you things like how the final data is encoded. Is it compressed? Is it 7-bit, 8-bit? Is there binary data, and that sort of thing. So that's what those bytes tell you. And then there's 7 bytes for a timestamp. And then the user data length, so that's A in this case. And then the actual user data. All right, so that, so you can see that's the kind of thing that we want to fuzz and we want to find bugs in, is data that looks like that. But, when I started this, some people told me, oh, you'll never find a bug in SMS because it's too simple, right? Well, for one thing, people still make mistakes in simple code, but it turns out SMS is actually more complicated than what I just showed you. So the last thing I showed you is the simplest possible SMS message. It's a text message. It says it's a 7-bit immediate alert, which means the data is 7-bit, and then do something when it arrives. So let's see what it looks like if you send binary data. That's more interesting. Like even Apple can't mess up sending just a text message. So binary data comes, the data portion of the SMS actually has its own header called a UDH, so user data header. And it looks like this. This is an example. So it's a little simpler. So it has a header length, in this case 5, an IEI, so that's a type. In this case the type is 0. And then a length of 3, and then the actual 3 bytes, which is the binary payload. In this case, 0, 3, 1. So let's see what this one means. So let's break out this example and see. And now you can start to see, well, maybe there might be some bugs lurking here because there's different types, and different kinds of data, and it's all binary, so it seems a little more promising. So this example is one I'll keep coming back to. This is for concatenated messages. So if you want to send someone a text message and it's more than 160 characters, you have a lot to say, you can actually do that. So you can send it, and it'll just break it up into multiple messages, and when it gets to the other end, it'll be put back together for the user, sort of like TCP or something. And so what this says is, I basically already told you this, but so the type is 0, which means concatenated message with 8-bit reference number. The reference number is like the ID for this message. So the next is, it's 3 bytes of data. The reference number, so this one's 0. So maybe I'm getting concatenated messages at the same time from 2 different people. And so that's why there's this reference number. Then there's the total number of messages. So expect 3 messages to put back together. And this is the first, so message number 1. They start from 1, not 0. So this is the first of 3 messages. That's what this data is telling you. And then there would be text, like, hi, how are you doing? Did you go to Ekoparty, whatever. So that's one type of binary data. What are some other ones that you'll see? And that was IEI of 0. IEI of 1 is one you get to tell you that you have voicemail waiting. IEI of 5 says that this is designated for a port. So just like TCP or UDP, you can actually register, applications can register for ports for SMS messages. It's kind of crazy. So on iPhone, port 5499 is used for visual voicemail. So it's that feature that like iPhones have where you can, see exactly all your voicemails and all that stuff. So this happens on that port. So and the data for a visual voicemail looks something like this. So it's got some sort of thing, and it's like a URL, and that's where the phone knows to go grab the sound file that it's going to listen to. And then port 2948 is also something. So anyway, there's different IEIs, and I reverse engineered and figured out exactly which IEIs it supports, and I think it supports 5 different ones, but I'm not going to go into that. And then finally, there's this program called PDU Spy, which is just a little Windows GUI, and you type in the PDU over to the right, and it breaks it out just like I showed you on the left. So this is like a great tool for when you're writing these. And so the problem is, like, almost every PDU that you find that like crashes the iPhone, like crashes PDU Spy as well. Although PDU Spy is better because it doesn't actually crash, it must catch its own exception or something. So it doesn't actually crash, but it doesn't help you. All right, so we now know SMS and what it looks like. So let's figure out how to fuzz it and find some bugs. Right, so I use Sully. It's a Python framework written by a couple guys who were downstairs in the tipping point booth. Sully does lots of things. It does test case generation, it sends test cases, it monitors your target to see if it crashes or something else happens, and it helps you sort through crashes. The only thing I used it for was to generate test cases, and then I did everything else by myself. And this, just like Spike was originally, it's designed to do block-based fuzzing, and which is perfect for this because it's a block-based protocol. And it basically has a lot of strings and stuff that different people have found to find bugs. So you can think of it, if you've never used it, it's better than Spike, which was written by Dave Itel. It's an immunity guy, so giving lots of shout-outs to the sponsors. So it's better. It's like way better than Spike. Spike was the first one, but it's Peach is probably more actively developed, so it's better. But I always use Sully. I'm an old guy. I can't learn new things all the time. All right, so let's see how we would tell Sully about some of this SMS protocol. So let's just take the phone number there. So I already talked about it. It's a link type value. So this was the example again. So it was like 7, some byte, and then some data. So in a Sully specification file, it would look something like this. So you tell it, okay, the first thing is the size. To compute the size, divide by 2, because it thinks 9. Sully thinks 9 by itself is a character. So this is like, to get the number of these hexadecimal ASCII things, you have to divide by 2. And then I say, okay, that size corresponds to this block of data. The first is a byte, and then there's another block, which is a string. So, and then I give a max length because, you know, it doesn't make sense to send SMS messages that are thousands of bytes long, because in real life you can't do that. All right, and then here's another example. So it's a little more complicated, so of UDH. So you know, you can check out the slides later, but it's basically the same thing. So you just describe exactly what each byte does, you know, which ones are size bytes to what blocks of data, and so on. And so eventually you get, you know, lots and lots of test cases. Sully, you know, generates, like, with these kind of information, tens of thousands of test cases to try. But the problem is, if I have tens of thousands of SMS messages I want to send to my phone, like, I have to pay, you know, 5 cents every time I send a text message. Or even if I have unlimited text messages, after I've sent the first couple thousand, my carrier is going to say, wait, there's something wrong, and they're going to cancel my account. So I have to figure out a way to send text messages to the phone without actually sending them, you know, to AT&T, who is my carrier. All right, so the other disadvantages of sending it, so even if I only had like maybe 100, and I was like, well, I'll send 100. Like, I don't want the carrier to watch me fuzz, because then they know all my test cases, and they'll you know, steal them and make my 0-day go away. So I don't want them to see. And the other thing is, like, I don't want to crash the carrier's devices. So, you know, earlier the talk 2 talks ago was talking about you know, how there's these bugs in carrier equipment, and, you know, I don't want to go to jail. So I don't want to test the carrier's equipment. I want to only test my phone. The other thing people are kind of working on is, well, maybe I just build my own base station. I don't know anything about hardware, so that's beyond me. So what I can do, though, is I can just inject it straight into the process that's parsing these. So the problem with injecting, though, is then every time they change the, you know, the new version comes out, I have to find where I inject it, and it's sort of a pain, right? So Colin and I came up with a better approach. So basically we just do man in the middle between the 2 applications, between the 2 processors, excuse me. So this has lots of advantages. I can do it locally over TCP. I can send them very quickly. It doesn't cost me anything. I don't need any equipment. And because from the receiving process, which is called comm center, it doesn't know any difference. It just knows it opened up, you know, a device, a raw device, and it started to read from it. So it doesn't care that it's coming not from, you know, the real network, but it's actually coming. It sometimes is coming from the real network because I'm proxying that, but it also could be coming from my TCP socket I opened. And you know, the carriers, the telco companies, they don't know that I'm doing this necessarily. Like, there might be some sort of residual responses that they're getting, but they didn't shut off my account, so I don't think they know. And the bad thing is, maybe you find a test case that actually crashes the phone when you do it through this man in the middle, but like if you really tried to send it over the real network, somewhere they would filter it. And that's true. I did find cases where the phone would crash, but if I really tried it over the real network, it wouldn't get to me. So the carriers do some sanity checking. So this is basically the way that you set up the man in the middle for comm center. So you find the plist file, which is like the configuration file for it, and you just tell it, oh, hey, by the way, insert this library into your process, which is the one that I wrote. It's pretty easy. And all this code is available at Moliner.org, which was the person I worked with on this. And then when you want to send a PDU now, instead of, you know, generating a text message or something, you can just use this little Python to do it. So you just connect over TCP, send a buffer, and that's it. So it's really easy to generate, or to test like tens of thousands of test cases. All right, so I have test cases. You know, I ran them. I found a bug, so I turned off my fuzzer and I looked at it, and this is what the bug I found. Oh, one more thing first. So again, you have to test these bugs to make sure they're real. So to do that, you know, how do I test this thing, right? So Colin and I wrote this little application that just sends text messages over the real network. And one point is like there were some carriers do different blocking than other carriers. So like maybe like there was one attack we had that Colin could do from Germany on the T-Mobile network, but I couldn't do from the U.S. on AT&T. So you have to check a lot of different carriers to see. And this is what the program looks like. It was on the iPhone, and you just tell it the command to, or the PDU you want to send, and it sends it. It's pretty cool. All right, so now here's the bug I found. This is what the crash report looked like that I got when I was fuzzing. And this is the one that they fixed in version 3.01. So they fixed it the day after my Black Hat talk. Of course, I had told them well in advance, but the funny thing is you'll see when I talk about how to exploit it, I think like people are like, well, why didn't they fix it? You gave them a month, right? And it's like, I explained why SMS bugs are really serious, because I can just send them and there's nothing you can do. And like it's just my theory, like they don't tell me anything, what Apple doesn't communicate. So my theory is they thought it wasn't, like you couldn't exploit it. Like, you know, it's one of these like exploitable, but like there's no way in hell you can actually write an exploit for it. So that, you know, they were going to say it's exploitable. I think that's why they didn't. And then like I never told them that, hey guys, by the way, I came up with an exploit for it. So I think when I showed up and I started talking about it, they were like, oh crap. So they like, you know, fixed it. So that was kind of cool. So, and you'll see why it's so hard. Like the exploitation over SMS is like really tough. Here's a quote from like my favorite movie, The Terminator. I don't know if you guys have seen that. But anyway, this is the bug basically. So it's so simple. So this is the data. It's the UDH header. If you just send 403 and then any 2 bytes you like, that's enough to make it crash. So it was a real simple bug. So let's see what the actual bug is. This is a reverse engineering of CommCenter, which is the process on iPhone that handles SMS messages. I called this function read next byte because it reads the next byte from data and returns it. And importantly, this function returns the next byte of data from the PDU, or if there's an error, such as there's not any more data, it returns -1 to indicate an error. So you can see over here, it's like a big switch statement for the different IEIs. This one is 0, concatenated short message. It reads a byte, gets the reference number, gets the total messages, gets this message number. So that's exactly what it does. The problem is they don't check for error. They don't check for the error return value. So what happens is if you send in, you say, hey, this is a concatenated short message, and then you don't give it enough data, it's like, okay, give me the next byte. It's like -1. Oh, -1 was the byte. Huh, that's funny. And then it's like, give me the next byte. Oh, -1, -1. And so it gets into problems because it starts thinking these -1s are data when really, you know, there was no such thing as a -1. So that's actually the bug. You don't send enough data. So this is just the same thing again. So again, read next byte returns the next byte or -1. If there's not enough data, you can start to do things like you can make this message number be -1. Or you can make the total number of messages to be -1. Or anything else. You could do things besides concatenated messages. That's just the one I chose. And it's the most exploitable one, I think. So this is more about the bug. So this is when you say, there's like a million denial of services in this, but this is the one that actually will lead you down a path that you can exploit. So this is when you give enough data that you say, oh, there's like 20 messages to expect, and then you don't give it any more data, and that means this message number happens to be -1. So it should have been like 1 or 2 or 3, but instead it's -1. So it gets into this code, and then it starts to like crash and stuff. And this is what the PDU looks like. So it says, like you can see that last 3 that's bolded, that says expect 3 bytes. So it says 1, 20, and then there should be 1 more byte, but there isn't. All right, so then what really happens is, this is the way the code works. So it reads the number that indicates how many total number of messages to expect. It allocates an array of C++ strings of that size. So that's how so you say, oh, expect 20 messages here, so it allocates an array of 20 D words that it's going to store pointers to each of the messages that come in. And then whenever a new message arrives, or whenever any message arrives, it says, okay, this is this one says it's the 5th message. So it looks in this array at the slot for the 5th message and says, do I already have something for this? So is this a pointer to the null C++ string? If it is, then it says, oh, this is a new message, so it copies it there. And if not, it says, oh, I already got this message, so it ignores it. The bug here is that, by the way, it explicitly checks that it's not too big for the array, and it's not 0, which would also be out of the array, because it decrements it by 1. So it actually does all the sanity checking it could do, except it never expected to get a -1. So when it gets a -1, it says, oh, this is the -1st message. Oh, okay, well then, let me look at the array position of -1, and then it starts using values from before the array, and then things go wrong. So two things happen with this, that eventually we're going to want to put some data there that we control and try to get control of the whole process. But we need to survive some stuff first. So the first thing it does is this compare. It needs to compare it to be the only way it continues on is if it looks just like the C++ null string, because that's how it knows that it hasn't received this message before, and then it actually acts on it. So we need to look at this compare function and figure out how we make this pointer look like it points to a C++ null string. And the way you do that is the C++ string structures, they have a length field, and then they have some other fields, and then they have data, of course. So you want to make sure that that length field looks like 0. That's basically what it checks. And so that means that whatever pointer happens to be sitting before this array, we need to ensure that there's a 0D word right before where that thing points to. So that's one thing we need to make sure that happens. So already you're thinking, this is going to be kind of hard to exploit. And you're right. Okay, so then the next thing that happens is it says, okay, this one was a C++ null string. Now I want to take the data that I just got from the wire and put it into the string, right? I want to make a copy of it. So the first thing it does is it calls this exchange and add, and then it calls destroy. So it basically makes a copy, and then it like frees the old buffer. So this is what I just said. So replaces the old string with a new string, adjusts some lengths, and then gets rid of the old string. And what this really boils down to at the assembly level is it thinks this is a pointer to a C++ string, even though it's not in this case. There's some reference counter in the structure that it decrements, and then it frees the actual data that goes with it. All right, so this is what we need to do. So we need to make sure that when this array is allocated, we control the D word right before it, because that's where it thinks it's a C++ string, but it's not. And I point out, really, we want to control the one 2 before it, because it actually decrements the thing beforehand. But anyway, that's a small point. And we want to make sure that thing points to something that begins with a 0. And then what we get out of it is it decrements a D word, and then it frees the pointer. And it turns out that basically either of those two things is enough to take control of the process. But it's hard. Because the question is, like, how, with like a browser vulnerability, you have JavaScript at your disposal, and you can like push like gigantic images into memory, and so you can control the heap a lot. But what about here? All I can do is send 140 bytes once in a while. Is that enough to like manipulate the heap in such a way that I control this pointer right before this buffer, and it points to something that has a 0 and something else that's important? And the answer is yes, you can do it. And the way you do it is with concatenated messages. So this is what happens when concatenated messages come in. I've already talked about this a little bit. So every time there's a new reference number, it shows up. So this thing, it thinks it's the beginning of a new concatenated message. It allocates an array of C++ strings. I already talked about that. So you can make it do that for different reference numbers, so you can get a lot of these buffers in memory if you wanted. And then each time that a new message comes in for any reference number, it obviously has to store that data somewhere. And so it makes these buffers of size basically up to 140. So obviously if I send in text messages to you, it has to store that somewhere. And the point is, if I send you text messages as part of a long concatenated message, it has to store those for a while. It can't get rid of them until they've all arrived. And so that's the way you can kind of start to fill up memory. And then once the message is complete, so say I was going to send you 20 messages, I finally send you the 20th, then it concatenates all those 20 together, so it makes a big string. And then it like prints it or something, and it frees it. And then it frees all the other ones. So all the little parts, all 20 little parts, and the big one, it frees all those. And that's it. That's basically what we can get with concatenated messages. So this is what we have at our disposal to attack the problem. We can allocate buffers of up to size 144, which just happens to be the size that it allocates for the data for our SMS message. And then based on by making it part of a concatenated message and either sending all of the messages or not all of them, we can make it stick around for as long as we want, and we can make it get freed whenever we want. It's making me dizzy how it's going up and down. And then also, we can allocate, by sending the new reference numbers, we can allocate these buffers of C++ strings. But it's a bigger allocation of 144, but still the maximum is only 1024. That's as big as we can do with that. And the data inside it isn't friendly, right? We can completely control the 144 bytes of data, but we don't control, the insides of those. It's just for the purposes of malloking. And then we can create like really long strings of up to 36,000, but they're very short-lived. They get allocated, they print, and then they go away. That's all we have at our disposal. All right, so I need to digress a little bit into how memory management happens. So there's different memory regions in OS X. The tiny one is for allocations smaller than 500. Then the small one for less than 15,000. Then there's other ones that we don't care about for today. And each of these regions contains a list of freed pointers. And the way that malloc works is the first thing it does is it looks to see if there's any freed pointer that's going to be big enough that it can just return that. And that's what it does. So if there's one exactly the size that's requested, it just returns it. If there's not one exactly the size, but there's a bigger one, it just splits the bigger one into two and returns the part you need, and then it puts the littler part on the free list as a smaller one. And that's it. That's the way basically the freed list works in these two regions. So the first thing you might want to do is a heap spray, because we want to try to arrange it so that we control the data right before this buffer that's allocated, so that when it underflows, it points to our data. So the way you can do this is you send a lot of SMSs that have so total number of messages is like very large, and then I just send in all the thises, except I don't actually complete it. So maybe I say, okay, expect a concatenated message of 250 different messages, and I only send 249. And so in this way I get so in this 140, which is 8C bytes allocated, which contains my arbitrary data. And I can do that for 8-bit references up to, I can't complete it all 255, I can do 254. And so basically I end up with 9 megabytes. So I can fill up 9 megabytes almost completely with my data. Like you can see in the second bullet point, for every 140 bytes, there's 4 that it uses for something that I don't control. So it's not like a total heap spray, but I control almost all the data. If instead of using 8-bit reference numbers, I use 16-bit, I can do even better. Then I can get 16 gigabytes of a heap spray, or 2 gigabytes of a heap spray. And the best thing is, the way that the phone works is, if I say I'm going to send 10 messages and I only send you 9, the phone doesn't display anything because it's waiting for the 10th one, because it doesn't want to display an incomplete message. It wants to wait for the whole thing to arrive. And so while you're playing around with the heap, the user has no idea you're doing it. There's no indication. So this is what the heap spray looks like in memory. So you can see these are 3 PDUs I sent, and I'm sending it. I told it to expect, I think, 64 maybe. And then I send it, oh, this is message number 1, this is message number 2, this is message number 3. And then after a while, when you send enough, at first, it's all over the place. This is the whole idea of feng shui, heap feng shui. So at first they're all over the place, but eventually if you send in enough of them, they start lining up one after another like this. And you can see, pretty soon I can control, large portions of the heap. So that's great. So you get an idea of filling up the heap. But what we really want is to make sure that when we allocate something, we control right before it. And so then you can do even trickier things. You can start to create holes in the heap so that when something next is allocated, it lands right in one of your holes. And the way you do this is you send in simultaneously 2 series of messages. So I say, okay, here's one, there's going to be a long message here with reference number 1 and a long message here with reference number 2. And I say, here's the first one for 1, here's the first one for 2, here's the second one for 1, here's the second one for 2, and so on. And so they start ending up in memory like, 1, 1, 1, 2, 2, 3, 3, and so on. And then at the end, I complete one of them. So it's like, okay, here's my 20th. Oh, I don't send you the 20th one for this one. And so one of those guys gets, his life objective is met. He's concatenated and printed and freed. And so what happens is then every other one on the heap is freed, but they can't be coalesced because still every other one isn't freed. And so I end up with lots of holes on the heap. Right, and this is what then this is what it looks like when you start to actually do the exploit. So I've created lots of holes with 41, 41, 41 in it. And then inside this hole, which is the blue is supposed to be the hole in the heap, I get this array of the C++ strings to store. And then, so you can see they're just all pointers to C++ strings. Actually, they're pointers to the null C++ string, because I don't have any data yet. And then when it tries to access array of -2, it thinks it's accessing a pointer to a C++ string, but it's accessing this pointer 41, 41, 41, 41. And so then it crashes. And it crashes right here when it's trying to do the compare. So it's trying to figure out like the length of this C++ string, and it can't dereference this invalid address, and so it crashes. And so it's like, okay, the heap stuff is working though. I was able to put data I controlled in front of this array that got allocated. That's awesome. All right, so now I'm confident that there's always two parts of this exploit, and it was really hard. It took me like 2 weeks nonstop of coding to get the exploit to work. So there was always 2 parts. One was, can I control the heap, which I can. And the second was, okay, what do I decrement? I need something to decrement that's going to get me a shell or something. So and it has a lot of restrictions. Like the thing I want to decrement, right before it needs to be a 0, right? So I get past the compare. I need to know where to decrement. It has to be some consistent address, and the lack of ASLR helps me there. Obviously, decrementing it should do something for me. So the idea is, okay, how about one of these pointers on the freed list? That's a good idea. The freed list basically is going to have a lot of zeros in it because there's not going to be pointers to be freed of every size imaginable. So there's going to be some zeros. If we decrement a pointer on the free list enough, so imagine that it's pointing to some freed buffer, and we start to allocate it, it's no longer pointing to a freed buffer, it's pointing to something. And if it's pointing to something we control, when it finally does want to unlink that thing, it's going to be, it's a typical, like an old heap overflow. So it's going to give me a write for primitive, because when it unlinks from the linked list, I'm going to get to do a write. Right, so this is the whole exploit, laid out. This is the idea. So we make sure our data is right before this array of C++ strings. Check, we already did that. We make sure that there's a pointer on the free list we want to decrement. We want to make sure that it's on it's on the free list, so it had to have gotten freed. And right before it is data we control. So when we decrement it, it starts decrementing into our data. So there's another restriction that we have to do with our heap magic, but we can do it. And we have to make sure, this is really important, that while we're doing all this stuff, this pointer that we're decrementing, it stays on the free list. We can't let it get used, or else it's not there anymore. So we decrement the pointer until it points no longer at a freed chunk, but into our data. And so the way I do that is I actually send the bad SMS 16 times. So it gets decremented 16 times, so it points like into my data. And then what happens is I need to get this freed pointer used. So I have to get a malloc to happen of that size. And then that gives me a write for, and so I have to overwrite something. I overwrite the global offset table, a value in it. And so then I have to get, so there's some now corrupted value there. And then I have to get that function called. So all this work just to own everyone's iPhone. And here's how I did it. So the first thing I do is I want to get the pointer that I'm eventually going to decrement. So I send in 2/3 of a small message. And then I want to start making the holes in the heap. So then I take, for n, I think I chose like 200. So I send in 2 messages, 2 long messages of size 200. I interleave them or whatever. I complete one of them so they get freed. So I have, approximately 200 holes on the heap. But, some of those holes get used up by things the iPhone's doing that don't have to do with me. And the other thing that's great is because I did a lot of allocations, I also cleaned out the free list. So there's now lots of zeros on the free list, which is I need as well, and I get that for free. And then what I do is, let's see, so that's the decrement guy. So then the next thing is I have to send, remember I sent 2 of 3 at the beginning? I send the 3rd one now, so that thing finally gets freed and it shows up on the free list. Then I start hammering it with 16 of these this -1 kind of SMSs, and every time I send one of those, it decrements. But I have to make sure, I basically have, each one's different, so I have to have at least 16 holes on the heap, and I have to control all the data. So everything has to work out just perfectly. Each one does a one decrement, so 16 of them. Now it's pointing well into my data. And now I have something on the freed list that is pointing to my data, and then I send in an array request for 7B, so I tell it, oh, here's a brand new reference number, and it's a 7B. And then it allocates, and all the great things in the world happen. So all I gotta do is, instead of sending in all A like I was before, now I send in data that looks like this. So the first line is when I just want to see what's happening, and just notice that in OS X they do this like checksumming of heap pointers. It doesn't actually stop you from exploiting, but it just makes you do one more line of work. So here I've sent in that, and this value 0048 ODC, that points to the thing in the free list. The free list is always at the exact same spot because they don't randomize anything. So if I do that, I'll get one thing, and then when I want to actually take control of the device, I need to put in the pointer. The thing I want to do the write for is some function pointer in the global offset table, and I used pthread mutex lock because it got called. All right, so then this is what happens with that first set of data I showed. So it crashes when it's trying to do the free because it's doing the write for. And it's actually trying to store dead beef into Babe Cafe. So I have complete control of the write for there. And then if you want to see what's going on, this first chunk, oh, by the way, I forgot to mention, like you notice I'm not using GDB, right, for these printouts. What am I using? I'm using iPhone debug, which originates right here in Argentina. So thanks to the core guys, if anyone's here, for providing iPhone debug, which is the cool debugger for iPhone. Anyways, this is what the free list looks like at this time, and so the one in bold is the one that so notice there's zeros in front of it. That's good. That's the thing I've been decrementing. And if you look at that in memory, the bottom line is where it used to point before I decremented it, 16, and that looks like actual a free chunk. That's what it was supposed to point to, but I pointed it up one row to my data. That gave me the right for. And then if I just send in slightly different data, then I end up with it does the right for, the global offset table, function pointer, and eventually it gets boom. Program counter is Babe Cafe. You know, yay, I win. So the one thing I have left out into this is I send the message, I get control of the program counter, and this process runs as root, and it is not sandbox. So I have complete control to do whatever I want on the phone. So it's pretty cool, which is why they fixed it. Thanks. So then the only thing to let you know the details on is, so this whole thing took 519 messages. That's quite a few. You only ever complete one, so the user only sees one message ever show up. If you mess up or whatever, you can just try again, because there's one SMS you can use one SMS to crash comm center. It'll start back up, and then everything's fresh, and you can keep trying. And even if you know you're under attack, there's nothing you can do except turn off your phone, and then you have to turn it on someday, and the thing queues it up. So one funny thing I did at Black Hat, so I got a volunteer from the audience who had an iPhone, and I said, so I was going to send the denial service, so I didn't want to take over their phone, I just wanted to send the one that crashes comm center. And when it crashes comm center, it takes like 5 seconds for it to start back up and get hooked up to the network and stuff. So the phone's basically like unusable for 5 seconds. And so I was just sending one like every 5 seconds, right? To show like no matter what, you can't use your phone right now. And so we were sending them throughout the whole talk, and like every once in a while we'd be like, hey, can you use your phone? Or I'd try to call him, I think, and it would say, oh, he's not available. And so. So this was all fun, right? And then after the talk, we turned it off, of course. We stopped sending the every 5 seconds. It was like 2 hours later, he comes up to us and he's like, he came up to Colin actually, and he says, hey, when are you guys gonna stop attacking my phone? I still can't use it. And it turns out like we were sending them and they were queuing up on the carrier's SMSC. And so like no matter what, even when we had stopped, it kept trying to resend them. And so his phone was just like hammered for hours. So it's kind of funny. Okay, so that was the SMS stuff, and then I have a few slides here about like, okay, so I got program counter, now what do I do, right? Because I could have just put shellcode in, but it won't run because they have dep and all that. So what can I do? Well, on iPhone 2, there was something you could actually do. So the way that the memory protection is supposed to work on 2 and 3 is once a page is writable, you can never make it executable. And so then the question I had was like, well, how the hell does the debugger work, right? Because that's how debuggers work. They change memory, and then they, for breakpoints, and then they have to actually execute. And so I just saw exactly how the debugger worked, and that was able to disable the dep. So as long as you could do a VM protect with a certain flag, then you could change your code. You could overwrite existing code. Like instead of setting a breakpoint in a library, you set like a big old shell code in the library, and then it'll actually run. And because they don't have ASLR, you could do return to libc, return-oriented programming, whatever to do this, and then you could get your shell code running. But you can't do this in iPhone 3. In iPhone 3, as far as I know, you can't get shell code running. So what did this do? Well, because of this, App Store programs could like update themselves, which Apple would hate. They don't want that to happen. And in reality, that's probably why they fixed it. Not so much because I'm out here preaching about shellcode, but they're like, oh shit, all the App Store things are gonna start changing what they're doing, and then we won't have tight control over it. I'm curious how they translated that curse word. So the other thing that I care about is I can run shellcode. And also, so the dynamic linker, it sits inside of each process, and I can change that too, because the same thing, I can just patch it with, instead of shellcode, I can patch it to do things I want. And one of DYLD's job on iPhone is to make sure you don't load unsigned libraries. And so I can just patch that out, and then I can load unsigned libraries. So that's cool too, because I don't want to write massive shellcode. I'd rather just write shellcode that patches DYLD, and then I can just upload and then link in a library. Then I can write in a high-level language, like interpreter. So there's going to be way better talk about Meterpreter than this. But just to let you know, it's just a payload. It was originally for Windows. It's actually better than a shell, so it's supposed to be like a shell. Like I really want a shell on my iPhone. It turns out this thing is actually, oh crap, my demo phone here is on critical battery. I gotta hurry. So besides a shell, it can upload files, download files, redirect traffic by what they call pivoting. And the cool thing on the iPhone is it gives you basically a command line. It's like a shell on a system that has no shell. So I mean that's why it's cool. Okay, demo. I have 10% battery, so I have to hurry. Like I say here, this is a 221 phone. I haven't jailbroken it. I haven't like set it for use for development. It's basically exactly like a phone anyone would have who didn't ever upgrade. Except I gave them an ad hoc thing, which allows them to run programs that are signed by me. Because I have to have without a 0 day or something, I have to have a program that has a vulnerability. So let's see here. All right, so this is a Meterpreter. I mean Metasploit command line here, and I just put in the command, and then let's hope it works. So on this phone, which is my test phone, I'm going to run the vulnerable program, boing, and then here I'm going to say, okay, go to town, Metasploit, come on, work. Ruby is firing up slowly. Okay, it started. It's transmitting. Look at that. Okay, so now let's see. So if you've ever used Meterpreter, you have to load up some stuff in it. So now I have lots of commands I can run. Except some of them don't work. Like execute, I think, doesn't work. But anyway, lots of them do. So you can do things like, where am I? Let's make it even bigger. So here is, oops. So like here's a system that like has no shell, but I'm running LS. It's like pretty cool. And then I can do what else is there? So like PS. So you can see like if you're like a total, you think I'm lying to you. So there's no, you can tell it's not a developer phone because it doesn't have like a debug server running. So there's Hello World. That's the thing I'm living in right now, and you can see that by saying get UID. I think is that what it is. Get PID. So yep. See, I'm really inside Hello World, and then I can do like I'm running as user mobile. And then you can easily write things in it to do like phone specific stuff. So it's even better than Meterpreter. So like my favorite one is called Vibrate. So I don't know if you can be able to hear this. Did you hear that? So and you can do other stuff. So like if I have one called that will dial the phone or will send SMS messages and stuff. But because this is like a legitimate app, it's in a sandbox, so it can't actually run those commands. Let's see. I think there's one like this. What is it? It's like, sysinfo. So this tells me like, the version, it's 221, blah, 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 blah. I think that's about all the commands I want to show you. But anyway, it's pretty cool. And this is like, Meterpreter on iPhone. All right, so just to say again, so they fixed this. This is something I talked about originally at somewhere in Europe. I was very tired. I don't remember, but it was in like April. They fixed it in version 3, and as far as I know, there's no way you can do this in version 3. But because they don't have ASLR, you can still just do as much return-oriented programming as you want. So you can still do stuff. You just can't do shellcode, and you can't do Meterpreter. All right, so in conclusion, SMS bugs are like really bad, right? If I could just send you a message and take over your phone, like, that's pretty devastating. Heat manipulation over SMS is hard. I'm sure everyone here will believe that after listening to all my slides. But you can do it, so it's cool. You can fuzz over local network SMS, so that's great. In theory, against a 221 phone, I could get a Meterpreter running on your phone by sending SMS messages that only sent by SMS and it's run as root. It's like totally powerful. And by the way that worked was So my shellcode got running using return-oriented programming, and then I patched DYLD, and then I got shellcode running by doing that, and then I had to load the library, and it was like really complicated. And every time I did that, I had to do it on top of an old library. It's really hard, but it works. And then finally, so iPhone is like pretty secure actually. If they had ASLR, they'd be really secure. But for now, you can just do return-oriented programming. You can still like do lots of bad things. So that's it. And please feel free to contact me if you have questions. Or the code's all available. The 519 SMS messages are available. They're all at molnar.org. So that's it. Any questions? Thanks. Questions. In English, please. I can't see any. Okay, I guess that's it then. Okay, thanks.